Hello, I am Christian Malaga, and this short video will introduce a few simple concepts related to the Fourier transform. The key concepts discussed are the idea that functions representing loads or response histories of arbitrary complexity may be modeled as a linear sum of sines and cosines, and the definition of the Fourier transform as well as why and how we use it. Let's recall that any periodic function can be represented by a linear combination of sines and cosines of the following form. Here, a sub k and b sub k are the amplitudes of the cosine and sine parts of the kth harmonic, and nu sub k is the harmonic's frequency. Besides, a sub naught is included to model any ordinate shift. Let's take the case of the force exerted by a pedestrian while walking as an example. If we measure this force, it will have a periodic shape like the one shown on the right. This graph presents the evolution of the pedestrian load over a time equal to the period of the action. Hence, the time values in the horizontal axis are divided by Tp, where Tp is the period of the load. Since the loading is assumed to be periodic, we can imagine that the same loading signature is repeated time and time again to the right. The vertical axis, which represents the magnitude of the load, is also normalized, in this case by the weight of the person. This loading can be modeled by means of a series of harmonics as presented before. In order to approximate the measured load, presented in gray on the left, with the summation of sines and cosines presented in red, a total of 5 harmonics are selected. Each harmonic will have its own period and amplitude, and the sum of all 5 of them results in the red curve on the top left graph. Since each harmonic has its own amplitude and frequency, we can express the whole series in mathematical terms. Moreover, we can organize this information in a tabular form where the first column k is the harmonic ordinal, the second column the frequency, the third column the amplitude of the cosine part, a sub k, and the fourth column the amplitude of the sine component, b sub k. Furthermore, on the basis of the amplitudes a and b of the cosine and sine components, we can calculate the amplitude of each harmonic as the square root of the sum of a sub k squared plus b sub k squared. This amplitude is a measure of the energetic content that is contributed by each harmonic. This information can be presented in a graphical form by plotting the amplitudes of each harmonic against their corresponding frequencies. We can see from this graph that the first harmonic is the dominant one, concentrating the largest amplitude of the set. Likewise, the third harmonic is associated with a very low amplitude, and we may get away with a good approximation even if we neglect its contribution. The previous exercise has allowed us to express a periodic load, that of a pedestrian, in terms of its frequency components, and we have been able to do this by expressing the load as a series of harmonics. However, this approximation, known as Fourier expansion, is only valid for periodic functions. In the case of non-periodic functions, we need a slightly more sophisticated tool, the Fourier transform. In general, the Fourier transform is a mathematical tool that takes a function in time, measures every harmonic component, and returns the information in terms of frequencies. It allows us to do what we have done before with the Fourier series, but now also for non-periodic functions. In other words, given the smoothie, it finds us its recipe. And the beauty of this is that it works for highly complex and transient signals as those coming from earthquakes, for example. On the left-hand side, we can see a history of accelerations recorded during the 1985 Mexico earthquake. By means of the Fourier transform, we can find its associated Fourier spectrum, shown on the right. This information in the frequency domain can be very helpful when explaining some features of the structural response. This picture, for example, taken in the aftermath of the 1985 Mexico earthquake, shows a collapsed building next to other mid to high-rise buildings of roughly the same age, which remain standing. This can be at least partially explained when looking at the spectrum of the ground motion. Notice, for example, the large peak at around 2 seconds. In fact, a disproportionately large number of buildings in this period range, corresponding to 18 to 20 stories, suffered severe damage during this earthquake. Let's now define formally the Fourier transform. The Fourier transform of a function f of t in the time domain is obtained by multiplying said function by a complex exponential with exponent minus 2p I nu t, where nu is the frequency, and integrating this product in time from minus infinity to plus infinity. Likewise, we can go back from the frequency domain to the time domain by means of the inverse Fourier transform, which is found by multiplying the function f in the frequency domain nu times e to 2 pi a nu t and integrating for all frequencies from minus infinity to plus infinity. In order to explain how we arrived to such expression of the Fourier transform, let's go back to our initial series of harmonics. Realizing that the trigonometric functions sine and cosine can be expressed as complex exponentials by means of Euler formulae, we can recast this expression for the time series in a new form, now defined in terms of a sum of complex exponentials with complex coefficients c sub k and frequency nu sub k. To make this transition, the following equalities must be satisfied. Notice that these demand the definition of the series from k equal to minus n to n, implying that negative frequency values must now be employed. Coming back to the case study of the pedestrian load, this change implies the conversion of this tabulated set of values to this new set. In it, you can see that instead of the 5 real values appearing on the initial table, we now have 5 pairs of complex conjugates, and hence harmonics, ranging from minus 5 to plus 5. Next, by means of the polar notation of complex vectors, expressed in terms of modulus and phase, we can express the series as a sum of complex exponentials from minus n to n, where r sub k is the modulus, and nu k and phi k the frequency and phase of the kth harmonic, respectively. If we now adopt continuous instead of discrete functions, we obtain the formula for the inverse Fourier transform, where the function in time f in t is the integral in delta nu from minus infinity to plus infinity of the function of amplitudes in the frequency domain, big F of nu times the complex exponential function. Now we know what each term of the inverse Fourier transform represents. The integral comes from the summation of harmonic contributions over the whole frequency range, from minus infinity to plus infinity. The complex exponential represents the harmonics, and capital F of nu is the amplitude in the frequency domain. A similar analysis can be made for the Fourier transform. The Fourier transform has some very important properties which are summarized in this table. The property of linearity, which means that adding up to functions in the time domain is analogous to adding their Fourier transforms in the frequency domain. The convolution and product theorems that establish the analogy between convolution and multiplication in the time and frequency domains. The shifting theorems that show that the effect of multiplying a function by an exponential at t0 in the frequencies is to shift the function by t0 in the time domain and vice versa. And scaling, which means that stretching a function in the time domain will translate into a compression of its frequency spectrum. Finally, let's find the Fourier transform of the Dirac delta function. This function, which as you may recall was devised by Dirac as an analogy for a point load, is denoted by delta of t minus tau, and defined to have values of 0 at all times different than tau, and take a value of infinity when t equals tau. Hence, its graphical representation will look like this. Besides, another defining property of the delta function is that its integral in time from minus infinity to plus infinity is equal to 1. The Dirac delta is called a function, but we can think of it also as an operator. This is because one important property of the delta function is that when multiplied it by a function f of t and integrating this product from minus infinity to infinity, it returns the value of set function f evaluated at the time at which the delta is located, in this case tau. Hence, this operation allows us to sample individual values of any function at the location of the delta. Returning to our problem, we need to find the Fourier transform of the Dirac delta located at the time a. To the right, we have the definition of the Fourier transform in terms of any function f of t. Replacing this f of t by the delta function, we obtain this expression. And recalling the definitional property of the delta as an operator, we find that this integral should return the value of the exponential function evaluated at time a. Therefore, the Fourier transform of the Dirac delta is a complex exponential. By the same token, the inverse Fourier transform of a complex exponential in the frequency domain will be the Dirac delta in the time domain. This finding will be very important in forming our understanding of the frequency content of harmonic and non-harmonic functions in time, and will guide our presentation of the Fourier spectra.